All right, so we are back for the third installment of our toxicity and water pollution discussion. All right, and what we're going to focus on today is discussing the remainder of the 7 water pollution types. So we've already discussed a few of those in the last lecture, right? And then we will wrap things up with identifying the various water quality tests that we do to test for certain types of pollution. All right. Many of these tests, not all, but many of them we will conduct as part of a lab exercise in class on stream water. All right. And then just so that you keep up with the reading, so all those various water pollution types and stuff we talked about so far, including in this lecture, are on pages 506 through 517 of the textbook. Okay. And that's not counting the stuff from chapter 7, the toxicity stuff, biomagnification and accumulation, etc. So also chapter 7. If you haven't done that yet. All right. So next type of water pollution is disease-causing agents. Mostly bacteria, but a few of them are viruses. And the most common cause of the spread of these is water that gets human waste in it, right? So infectious organisms originate in the waste of infected individuals. Somehow that waste makes its way to our waterways and causes any one of these kinds of nasty diseases. All right, so typhoid, cholera, bacterial dysentery, etc., etc. A lot of these are waterborne and originate in human waste. So if there's not the right types of treatment of human wastewater, then we can end up with those nasty critters in our water. And when we drink the water, it gets into our intestines and wreaks all kind of havoc. All right. One of the tests that we run for disease-causing agents is what's called a fecal coliform test. All right. This is one of the ones that we probably won't do just because of lack of equipment and time. But the way that works is you run water through a little filter. So that's what this is. And the filter does have little grids on it. And in doing that, you place the filter paper on top of a growth medium, which is some sort of agar there. And that agar, what it does is it allows the bacteria that will be on the filter, you just set it on the growth medium, and any bacteria present will get transferred to that growth agar and create these little colonies. All right? And there are Clean Water Act and Safe Drinking Water Act standards for the number of colonies you can get per unit of area, right? So all water is going to have some bacteria in it, right? Bacteria is just part of our daily lives, you know. Not only could we get rid of all of it, we probably don't want to. A lot of that bacteria is good bacteria. But if you get lots of bacteria growth from a water supply, then there's a higher probability that some of that bacteria is the bad kind. All right? So there are standards for how much bacteria we should be seeing in a water supply. All right? Next type is what we call sediment pollution. So a stream ecosystem with low level of sediment is going to have good light penetration, right? And that's the kind of the normal state. So most of our streams up here in the Northwest and most of our bodies of water, lakes, etc., have great light penetration, right? Which does help with temperatures and dissolved oxygen too, although indirectly, all right? And so when we get sediment pollution, what we look for in that water is lots of suspended particles in the water. Now, after like a big rainstorm, like Yellow Hawk Creek, I don't know if you guys pay much attention to that, but after a big rainstorm, you should notice that Yellow Hawk Creek frequently has a high degree of sediment pollution, right? So it has sort of that milky color. And the reason we call it pollution is not because we're just getting sediments in the stream, but probably an excessive amount. Okay, and that's because of neighboring agricultural land or deforestation, etc., where the vegetation is not as able to hold the soil in place, and so we get an excessive amount of runoff into a stream, carries with it an excessive amount of sediments when the sediments are not held in place. Okay, and some of the problems with that is it's going to limit the light penetration, which is important for the plant growth and photosynthesis. Many of the plants and animals that burrow or attach to rocks, right? Those rocks get buried by the excessive sediments, okay? And many of the toxins like lead and mercury that maybe are not normally soluble in water are attached to those soil particles, and so we actually bring some of those toxins, those insoluble toxins, into the water as they are attached to those sediment particles. All right? And again, the major concern here is not the natural erosion of sediments into waterways. That happens even after a big rainstorm and there's no deforestation or agricultural fields. We get a slightly less penetration because of sediment. So we're just talking more about the excessive amount because of land use practices. All right? And then we have organic compounds. Now, a reminder, we've talked about this word organic and how it differs in the world of agriculture from the world of chemistry. So, in the world of chemistry, which is what we're referring to now, are compounds that are based on the element carbon. So carbon kind of has its own special branch of chemistry because it is a little unique in the way it bonds and creates molecules. All right? Organic compounds are natural in some cases, so sugars, amino acids, oils, lipids, all those kinds of things. All biomass is technically organic or carbon-based. All right? Other types of organic compounds that are synthetic, though, would be many of our pesticides and solvents and industrial chemicals, plastics, right? So these are organic compounds that are synthesized in a lab and do not occur naturally. Okay? Health concerns with organic compounds, again, it depends on what we're talking about. Some organic pollution leads to eutrophication. Okay? Some organic pollution leads to toxicity issues, right? So pesticides like albicar, for example, if that builds up too high, that can attack somebody's nervous system. Some of our nasty solvents are associated with blood disorders and like cancers and things like that. Okay? So the word organic, you got to remember, in the world of pollution and chemistry, it does not necessarily mean it's safe or okay. And then inorganic chemicals refers to the classes of chemicals that are not based on carbon. So acids, salts, and heavy metals would all be part of that. And some of our big concern with inorganic chemicals is they have a tendency to bioaccumulate, right? So things like lead, which are found in old paint and industrial pollutants. We used to use leaded gasoline, which we don't anymore. Mercury has a tendency to bioaccumulate. So big concern with mercury levels is in things like our top predators like tuna and swordfish. All right, so we tend to see excessively high levels of mercury, and mercury is a neurotoxin. Causes all kinds of issues with people's nervous system if we get some mercury poisoning. All right, and then last is our radioactive substances, a much more rare form of water pollution, at least here where we have controls. So we've talked about radioactive substances way back in our nuclear energy chapter, but we're just talking about isotopes that emit radiation, right? So they have an unstable nucleus and they emit like alpha or beta or gamma radiation, right? And some of the sources of radioactive substances, we sometimes can see some excessive exposure in mining facilities, medical facilities, because we do use there's what's called radiomedicine, right? So we use like radioactive dyes, etc., for some of the medical procedures like MRIs and things. Nuclear power plants, of course, are a source of radioactive pollution. And keeping in mind that some areas do have natural rates of radiation that are a little bit higher than others. All right? And what would be our concern with radioactive pollution? That would be cell damage, damage to your DNA that may end up causing things like cancer and stuff like that. Not very common that we see acute issues from radioactive substances in water, right? Usually that's when people are in a nuclear reactor in an emergency setting. So if you're getting radioactive substances in water, you'd be dealing with more of those chronic exposure issues like cancer. But remember, these chronic issues are really hard to link back because people get cancer anyways. It's hard to know exactly what caused it. All right? Now, going on to water quality tests. At this point, we're only going to identify what they are. We will talk about these in more detail during class and also run many, but not all of them. All right? So if we wanted to test for sewage pollution, the most common test we would do is a fecal coliform test, that one that was actually already described to you. We could also run a nitrate and phosphate test. We would expect to see increased levels of nitrate and phosphate, although that could also be due to fertilizer runoff as well. All right. For sediment pollution, we run what's called a turbidity test, right? And that's essentially shining a light or laser through water, and we're counting essentially the device counts, not the particles, excuse me, the amount of light that gets scattered by sediment suspended in the solution. All right. Inorganic plant and algal nutrients, again, we could run nitrate and phosphate tests. We can do that chemically or using probes. Inorganic pollutants, right, would include some of those water-soluble materials we talked about. And the way we would measure that is what's called a total dissolved solids test. And we use a conductivity meter. Now, those of you who took freshman science at Lowell High School, you've actually used a conductivity meter before. And then we could also run what's called a biological oxygen demand test. And what we do for that, when we use a dissolved oxygen probe to measure the dissolved oxygen, what we do is we do a 2-point measurement. We'd measure it when first collected, and then we put it in a dark area, so any suspended algae or whatever wouldn't be able to undergo photosynthesis. All right, and then what we do is we measure the dissolved oxygen again, maybe a day or two later, and in doing so, we'd be able to determine how many organisms in the water are consuming oxygen, because we wouldn't be producing any extra because there'd be no photosynthesis going on. All right, and then of course for thermal pollution, this is one of the tests we will also run. You just do a temperature comparison between 2 points. Typically, you want to have at least a mile or two in between. And normally, we would run a thermal pollution test. Near somewhere like a power plant, or if you're worried about excessive clearing around a stream and the sun heating the water up too much, right? You'd have to do a 2-point measurement, maybe several miles apart, but also during the summertime when the sun's actually going to make a difference. So we'll do a thermal test on the stream, but we're not likely to see much of a difference in temperatures because it's just not warm enough yet. All right. That concludes this little lecture, right? So we're going to be just shy of 15 minutes. Make sure you guys do some of the follow-up reading, though. Okay, that's going to be important.